do the honor. All right, so it is my pleasure to introduce Greg Eyink for our program. Greg spoke earlier in workshop number 1, and today he is going to give us a seminar about Navier-Stokes is wrong, what? At Sub-Kolmogorov scales and why it matters. Okay, Greg, so sorry about this delay. So it's like we are 10 minutes late. So maybe if you can finish at 5 plus, and then have questions, that'd be great. Thank you again. Sorry.
Okay, no problem. These things happen. And again, I'm sorry that I couldn't be there. I guess this was the 3rd Newton program that I participated in. It was always fun to be there in person before and talk to people, but well, we do the best we can under the circumstances. This is actually going to be a direct continuation of my talk in January, and I'm just going to elaborate on a particular part of that talk. This is a quick reprise of what I was saying there, which is that I was arguing that thermal noise effects already appear at and below the Kolmogorov scale. Therefore, the turbulent dissipation range in real molecular fluids in nature is not accurately described by deterministic Navier-Stokes. And I want to emphasize that there are no experiments at all validating Navier-Stokes at and below the Kolmogorov scale. Luckily, computational power is sufficient now that people can do numerical simulations, including these thermal effects. So both for fluctuating hydrodynamics, that was done by John Bell. And that's this, I think people can probably see my cursor. That's what I show here on the left, was he did a simulation of turbulence in basically a glass of water, 5 centimeter cube square container of water, actually watered glycerol, around room temperature, pretty vigorously stirred. So the energy dissipation is comparable in the upper ocean mixing layer. And sure enough, what you see is the thermal spectrum, the thermal equipartition spectrum, K squared, that comes out of very simple statistical physics arguments appearing right around the Kolmogorov scale. In fact, in their simulation, it actually occurs above the Kolmogorov wave number by a factor of about 2 or so. And then since that work, there has also been another simulation. This was for a liquid. There's also been a DSMC simulation. This is direct simulation Monte Carlo. It's a molecular gas dynamics method. And they have observed exactly the same thing now for turbulence in a gas. They actually did a Taylor-Green vortex simulation and also observed exactly the K squared spectrum. So these simple statistical physics arguments are pretty well corroborated now. And I think in the future, we'll see more and more of these because now that we have the computational power and people have started realizing that something interesting is happening there, there'll be more of these. We also looked in our shell model work at the far dissipation range and looked at what was predicted by Kraichnan and others. And we found that it's just completely wiped out by thermal noise. And so this strong intermittency that you see in the deterministic case over hundreds of orders of magnitude gets completely wiped out when you put in thermal noise, and all the statistics becomes boring to leading order, boring trivial Gaussian statistics. And this is what John Bell also saw in his simulation when they looked at higher order velocity gradients, so high derivatives of the velocity gradients. And what you see in the colors here with the solid lines are the Navier-Stokes results. So they did a deterministic Navier-Stokes simulation, and they see what everybody else does, that as you increase the order of the gradients, the probability distributions become more and more flared, more and more intermittent. But as soon as you turn on the thermal noise, all that disappears, and you see beautiful parabolic profiles in this log plot, which indicate that the statistics of the higher order gradients in particular is just Gaussian. And so what I want to say is that all the nice theorems that have been developed for high order gradients in Navier-Stokes, Whereas and Guillaume and Tamam and others describe this stuff, they're talking about those gradients. And in the real world of molecular fluids, that's not what happens at all. As far as we can see from these simulations, it's just Gaussian thermal noise to leading order. I mean, there's other intermittency effects competing with that, but that's to leading order. Okay, so, but then you might still ask the question, why does it matter? So what? Does this actually play a role in any physics? And to that, we can only say that thermal noise is known to play a very important role in microscale physics in lots of other areas. I mean, so for combustion, droplet and bubble formation, biolocomotion of microorganisms, polymer dynamics, high-Schmidt mixing, in all of those cases, it's known that thermal noise plays a very important role in laminar flows. And so then this leads to the obvious question, what about in turbulent flows? And I'm going to focus on just one of those cases here, which is the case of high-Schmidt mixing. And there are several reasons for that. One is that there are lots of indications that in high-Schmidt mixing, particularly mixing in liquids, that thermal effects are very important. And one of the oldest is the Stokes-Einstein relation, which I'll talk about all these things in more detail. But in particular, the Stokes-Einstein relation for the diffusivity actually contains the thermal energy. And then there also are giant concentration fluxions, which are a direct manifestation of thermal fluctuation effects going up to macroscopic scales that I'll talk about. Furthermore, there's very convenient theory that has been developed to understand these, and in particular, work by Donev and vanden-Eijnden in 2014 that make a really nice link with turbulence theory. And so this made it sort of the simplest, most obvious case where one could go ahead and make some predictions about what's happening, get some idea of how the thermal noise might play a role. And so what I'm going to be talking about here in the first part of the talk is how to extend this work of Donev and vanden-Eijnden to the case where you have turbulent mixing. And I'm going to be reporting on what's in this preprint here. Okay, so I don't have to say too much for this audience, I think, about the Batchelor-Kraichnan theory, but that's the backdrop of what I'll be discussing. The most important thing is that the Batchelor-Kraichnan theory all takes place below the Kolmogorov scale. So, it discusses the traditional view is it's described by an advection diffusion equation. You have this red spectrum. Let's consider this as the energy spectrum. It's actually the Schmidt-1 scalar spectrum in this plot, but it's essentially the same as the energy spectrum. So here you can see the energy spectrum, and then this Batchelor range all happens below that. It's driven by straining at the Kolmogorov scale, which I'm going to call gamma. And then this drives a scalar cascade down to the so-called Batchelor scale, which is defined here in terms of the diffusivity and the straining rate. And the important thing is it's a factor of square root of Schmidt smaller than the Kolmogorov scale. So that's where all the action is. And there's this 1/k spectrum predicted by Batchelor that extends down to the Batchelor range. And then the spectrum is supposed to rapidly drop off. And so, I mean, this is, I think, one of Batchelor's nicest works. I mean, this is, I think, is one of his masterpieces. And it's famous in the turbulence community as a rare thing in turbulence, to quote from Bob Kraichnan, where you could get exact results. And so Batchelor predicted a rather detailed spectrum. In addition to this 1/k in the so-called viscous-convective range, so that's between the Kolmogorov scale and the Batchelor scale, you get 1/k. But he also predicted in the viscous-diffusive range below the Batchelor scale that you would have a Gaussian type decay. And he assumed for this a velocity gradient that was constant both in space and time and dominated by Kolmogorov scale eddies. Kraichnan took a different point of view, and he said, well, he thought it was better to approximate this as constant in space because everything is smooth below the Kolmogorov scale, but still rapidly varying in time. And he recovered Batchelor's prediction of the 1/k spectrum, but then said, no, the decay in the viscous diffusive range, above the Batchelor wave number is exponential, not Gaussian. And so this was the big controversy or the big disagreement between their two theoretical approaches, is that they were arguing what actually happens below the Batchelor scale. Okay, so as far as experiments and simulations, I mean, this 1/k has been observed in quite a few experiments now. There's still, the experimental situation is still not completely clear. I mean, there are a number of experiments that have failed to see it. But there's pretty wide agreement that you do see this 1/k. I mean, the latest experiment that I know was one just last year by Iwano et al., and that's what I'm showing here, where again, you see in green the Kolmogorov, I mean, the turbulent velocity spectrum with a Kolmogorov range. Then below that, but actually well above the Kolmogorov scale, this is actually quite well known that the decay of the spectrum below the 5/3 happens above the Kolmogorov scale. And so you actually see the 1/k happening above the Kolmogorov scale when the velocity first starts decaying rapidly. And in this experiment, they've managed to resolve almost down to the Batchelor scale. And so I think this is the best result so far, but they have noise in their measurements and they cannot resolve down to the Batchelor scale and below. And so there are no experimental measurements of that regime at all. People can, however, do simulations, and they observe both the 1/k. So I think the latest work I know is that of Clay in 2017. He was a PhD student of P.K. Young. I'm showing, however, Goto's somewhat earlier data, mainly because it shows really nice agreement between the Kraichnan theory and the numerical simulation. And so they look at a compensated spectrum. You can see this flat part corresponds to the 1/k. Then it decays down, and you can see that Kraichnan's theory, the green, fits their numerical results quite well, and they went up to Schmidt numbers of about 1,000. Okay, so the point is that this viscous diffusive range is so far only accessible by simulations, and the simulations favor Kraichnan over Batchelor. Okay, so I'll just remind everybody quickly what Kraichnan did to make his predictions. This is now quite well known, and I'll just go through it quickly, is that he assumed that the velocity field was white noise in time. And in particular, for the Batchelor range, you choose the spatial covariance so that the R dependence is R squared. And so this corresponds to a constant spatial gradient assumption. And this factor gamma there corresponds to the inverse of the Kolmogorov time. So once you made this into a Gaussian white noise, then of course you have to specify your calculus. And it's natural here, since you're considering the physical limit of a very short correlation time, that this becomes Stratonovich. And that's the so-called Kraichnan model for passive scalar advection, is this equation, to which you can then add a random source or some other form of driving scalar fluctuations to create the cascade. So once you go to Ito, then of course that creates an eddy diffusivity here. And the important thing about the Kraichnan model is that there's no closure problem for the correlation function. In fact, all the higher order correlations of the scalar obey closed equations. And so it then just becomes a mathematical problem to solve those equations. And I think most people here notice that there was a sort of revolutionary period for this model in a decade from about 1995 to 2005, in which there was an enormous development begun by a paper of Kraichnan in 94, and then continued by Goetsky-Kupiainen, Chertkov, this was Chertkov, Falkovich, Lebedev, all of those collaborators, Schreiman and Sidja, and they studied many elaborations of this, the inertial convective range, many things. And you can see reviews of all those developments here and more besides in these references. But just focusing on the Batchelor regime in this time period, there were extensions to finite correlation time. So it was understood how you go from the Batchelor frozen velocity field case to the Kraichnan white noise velocity case. There was a lot of work in the physics community on that. And more recently, there's been a beautiful work, a rigorous mathematical proof of Batchelor's 1/k spectrum in a forced 2D Navier-Stokes flow by Bedrosian, Blumenthal, and Pouchon-Smith. That was just a couple years ago. So that's, again, a really nice confirmation of Batchelor's original ideas. And so I would say in terms of theory, simulation, and experiment, pretty much everything confirms the Batchelor-Kraichnan theory.
Can I ask you a question, Greg?
Of course.
Could you go back one slide? And you mentioned this last equation is like you say, it's a deterministic PDE. is there also a set of equations for the fluctuations?
Well, I mean, there are closed equations for all higher order correlations. So in that sense, yes, right? Because you can say, I mean, there's no, I mean, the model, of course, is a model for the fluctuations right here, right? And it's known that this equation has strong, in the probabilistic sense, strong solutions. There's been a lot of nice work. There's been a lot of nice work on the theory of this equation, and it's known that you have strong statistical solutions of that equation. Another way of saying that is that there's no Eulerian spontaneous stochasticity for this problem. Once you specify the velocity, the noise, which is this random velocity, there's a nice, unique, strong solution to the problem, even if you set the diffusivity to 0.
Yeah, I like this a lot. It fits exactly into my theory.
Okay.
For transport noise. And
Okay.
I didn't realize that you had a way of closing it, because somewhere along the line you have to have had taken the expectation in order to get that.
Right. Yeah, and of course, so the first person to realize it, you get closed equations. Well, Kraichnan and then independently, Kazantsev in the Soviet Union did the same thing for kinematic dynamo independently, about the same time, 1968. And probabilists also did it. So there's also a huge independent literature on this in the probability theory, where they call these Brownian flows. And these two literatures have now sort of merged together. Okay.
Well, thank you. Thank you very much, Greg.
Okay. Okay, so, but I want to raise some serious questions about this. So I already mentioned the Stokes-Einstein relation. This began with Einstein's work in 1905, in which he looked at the diffusivity of a hard sphere moving in a fluid and applied his general fluctuation dissipation relation, his Einstein formula, to that particular case. And then you get this Stokes-Einstein relation for the hard sphere particle. But it was realized after Einstein's work over a period that this relationship is much more widely valid and holds in general for liquid diffusion, high-Schmidt advection, where this Stokes-Einstein relation holds to a quite good approximation. So this was discussed in particular by Onsager in a very seminal work in 1945. This is the work where he introduced what's called the Onsager-Fick formulation of multi-component diffusion. This was in some ways the basis of his Nobel Prize, because this was one of the cases where they could, using this approach, experimentally verify the reciprocal relations. But in any case, what he said in this paper was that the ratio, where you're looking at this ratio here, is a length of order the magnitude of molecular dimensions, normally smaller than this value 6 pi eta, what I called 6 pi sigma. From the point of view of molecular theory, viscous flow and diffusion present parallel problems. It would seem that for an exact theory of either, we should have to analyze the cooperative character of the molecular motions involved. But this difficult analysis has not yet been developed further than the hydrodynamic approximation. And the work that I'm going to talk about by Donev and vanden-Eijnden is one attempt to tackle this problem that Onsager was talking about here. And I'll just mention as an historical aside that this was, of course, the same year in 1945 that Onsager was also working on turbulence. This is when he published his 1945 abstract on turbulence and wrote his letter to C.C. Lin and von Karman. And so this was at the same period. And so now it's sort of interesting to try to join these two things, the Onsager work on turbulence and this. This is still a very active area of research. There's a lot of work in statistical physics and physical chemistry to this present day, talking about extensions, modifications, et cetera, of this Stokes-Einstein. Okay, so another important clue comes from what are called giant concentration fluctuations. And this is a more recent discovery. It was only found experimentally in 1997 in this Nature article of Vallati and Giglio. And it's part of the general fact that you get long-range correlations, long-range thermal fluctuations in states that are not in thermodynamic equilibrium, in global thermodynamic equilibrium. They can be locally in thermodynamic equilibrium, but when they're not globally in thermodynamic equilibrium because of imposed gradients, you generally get long-range correlations. And this has been known for decades now. In this particular application, when you have an imposed mean concentration gradient, then the equilibrium, thermal equilibrium fluctuations of the concentration, which are normally very small, those are shown in this figure here by this dotted line, are hugely enhanced, and they become really gigantic, orders of magnitude larger, and they are governed by this power law behavior. So this is what's called the structure function. This is what statistical physicists typically study, and you get this k to the -4. And just to make contact with the standard turbulence literature, it's usually you look at the energy spectrum, which is k squared and then some multiple of this. And so the spectrum that would be looked at in turbulence theory is this quantity here, k to the -2. And just to emphasize, how these are really macroscopic, I show a photo from this paper of Valati and Giglio, and it shows the scale. This is 1 millimeter. And so you are indeed just sub-millimeter. And in this original experiment, which was done on Earth, the reason it didn't go higher was because it's quenched by gravity. So this k to the -4 region here is quenched by buoyancy effects. And if you go to microgravity environments, then this just goes up to the scale of the apparatus. And so you can get truly macroscopic thermal fluctuations in this problem up to millimeter scale and above in microgravity environments. And what Valati and Giglio said in their paper was, I'll quote them, so the orders of magnitude increase of the fluctuations above the equilibrium value, the most prominent feature that can be captured experimentally, is to be expected for any non-equilibrium fluid that has macroscopic concentration variations comparable to those in this experiment. And so I think emphasize again, in any non-equilibrium fluid, including in a turbulent flow, where you'll have concentration gradients created by the concentration fluctuations that you're injecting. And so you should expect these kinds of effects there. It seems almost obvious that they should be present. Okay, so now I want to discuss some of the analytical theory that's been developed for these, and particularly this work of Donev and vanden-Eijnden, who developed a theory for the high-Schmidt mixing only for a fluid at rest. And the starting equations are Landau-Lifshitz fluctuating hydrodynamics of a binary mixture. So that's more or less standard in the statistical community. I give some references here if you want to read more about that. One thing that they did, which is a little bit avant-garde or not completely orthodox in that literature, is that they assumed that for molecules that are sufficiently large, like colloidal particles and so forth, that they're not going to fill the full advecting velocity field. They'll only fill the advecting velocity field with the scale smaller than the radius of the molecule removed. Okay, and so they took that step. And then the rest of it is the standard thing. The one thing that I want to say is that these white noises are not real white noises in space. They can be considered, if you wish, white noises in time, although you could put a frequency cutoff as well, but they're definitely not in standard Landau-Lifshitz theory white noises in space. These are not stochastic PDEs. So when you're applying Landau-Lifshitz equations, everybody that uses those knows these are not stochastic PDEs. They have a cutoff in, and indeed all the transport coefficients depend on that cutoff. If you change the cutoff, you have to change the transport coefficients. There's a renormalization effect. And so these have to be regarded as low wave number effective theories that are only valid below some cutoff, which is more or less arbitrary. Okay, so what Donev and vanden-Eijnden did is they then looked at the high-Schmidtnumber asymptotics by scaling with a parameter so that the viscosity is large, the diffusivity is small, and this is carefully arranged to be consistent with the Stokes-Einstein relation here. So you know that they should be inversely proportional. And then they also look at a fast timescale. So this goes back to the Onsager quote. It's known that in liquids you have very slow mass diffusion, but very fast momentum diffusion. And that's just for lots of I mean, this is more or less understood. You have a caging effect of the molecules. And so molecules have a hard time moving, but it's easy for them to transfer their momentum to other particles by collisions. And so you have a big separation of scales, and momentum diffusion and mass diffusion are coupled in sort of a reciprocal way. And so on this long time scale, they changed these variables. They did this asymptotics, and I'm not going to go through the formal calculation. I'll just say the result because it's rather intuitive. When you turn the crank on the asymptotic method, what happens is that this advection becomes a white noise. And so you get, interestingly enough, a Kraichnan model. Only now this Kraichnan model is sort of not an ad hoc proposal. It's an exact, I won't say rigorous. I don't think that they did their work in a mathematically rigorous way. It's still formal asymptotics, but it's a formally exact expression of this high-Schmidt limit of the starting Landau-Lifshitz equations for the problem. And then this.
Right, before you used that symbol before the circle with the dot, and you gave it a name. You said it's the one, the red one.
This one?
There, yeah. And you told about what is that again?
So that's Stratonovich. So the point is that you have, since this thing becomes white noise, delta correlated in time, it would be ambiguous not to specify what stochastic calculus is involved. And so you have to use Stratonovich calculus here because this, I mean, this just comes out naturally from the analysis, but also it's known generally that when you start off with a problem with a finite correlation time and you take the time correlation going to the limit, you do not get Ito, you get Stratonovich. And that's what happens here. So this is the Stratonovich interpretation of this stochastic PDE. Okay, although it's not really a stochastic PDE, it's really a bunch of stochastic ODs because it's still cut off at high wave numbers. Okay, but you have to specify the stochastic calculus. And then this, I hope that answered the question. So then the space part actually turns out to be very simple. The thermal fluctuations of the velocity in this limit simply become slaved through the Stokes operator. So the viscous diffusion slaves those thermal fluctuations. And so you get this instantaneous balance between this W and the thermal fluctuations. And so you simply have to solve this stochastic Stokes equation. And so this gives you directly this covariance. Once you implement that filter and you use the Oseen tensor, which is the Green's function for the Stokes operator, that specifies this covariance of this W field in this white noise here. And so the nice thing is you actually get a version of the Kraichnan model out as an exact representation of the thermal fluctuations in the high-Schmidt limit. Okay, so the analysis of those guys, then they say, well, now we have this equation, we can start to analyze it. One thing that you get immediately is when you switch to Ito, well, then that creates this new diffusion term. You get a renormalized diffusivity. This is just like what happens in a turbulent flow, except now this is an eddy diffusivity created by thermal eddies, thermal fluctuations. And very nicely, as you might expect from their analysis, that with assumptions of their analysis goes beyond homogeneous and isotropic cases. It can cover the more experimentally interesting cases where you don't have those. But under assumptions of homogeneity and isotropy, you get out directly from their theory, the Stokes-Einstein relation, plus a correction, which is actually well known from molecular dynamics simulations of these problems, is that there is such a small correction, although it's very tiny because this is the size of the molecule, the solute molecule, divided by the size of the system. And so it's a very tiny correction in most macroscopic situations, but they reproduce that as well. And they also, of course, can solve their limiting model numerically. So since they get this reduced model, they can do numerical simulations with both of them. And this illustrates how their scheme captures those giant concentration fluctuations. So they start off with this problem where the blue and the red represent different mean concentration, different concentrations. They let it evolve. And this one is corresponding to the original Landau-Lifshitz equations. This one corresponds on the left to their reduced model. And they can reproduce all the same features that are seen in the simulation of the full model with the reduced dynamics at a factor of Schmidt number less work. So the bigger the Schmidt number is, the less expensive their numerical scheme is. And so the whole point of their work was to come up with this much more efficient way of computing these effects without, because it's a stiff problem otherwise. It's very expensive to compute this with the original Landau-Lifshitz equations. Okay, so what I want to do now is I want to extend this work to the case of turbulent high-Schmidt mixing. So our starting point is going to be very similar, except now we're going to start off with the full nonlinear Landau-Lifshitz equations, only considering the low Mach number limit here and the isothermal case, not the general case. Other than that, I'm doing exactly the same as what Donev and vanden-Eijnden did. Then, however, we have to say, but we're in a turbulent flow. And so we say, okay, but we're going to break this velocity that appears in this equation into two parts. And this is sort of the standard thing that people generally do in fluctuating hydrodynamics. I don't know that's ever been done for a turbulent flow before, but it's sort of the natural thing to do. You look at the deterministic equation, which of course is not continuum Navier-Stokes, it's cutoff Navier-Stokes. But you take that deterministic equation, you solve that, and then you linearize around that solution, and that's the equation for the thermal fluctuation. So that gives you this without any approximation at all. And then you look at this nonlinear term, which is the term of the thermal fluctuations interacting with the thermal fluctuations. And you can easily estimate that just by knowing the size of those thermal fluctuations of the velocity, just a simple central limit theorem argument. You plug in the kinetic theory estimate for the viscosity. That's where this ultimate estimate comes out from. And this is all done in 3 dimensions, by the way. That's dimensionality is important in this game. And what you find is that as long as the length scale that you're considering is bigger than this one, where this is the inner particle spacing, this is the mean free path. And in a gas, the inner particle spacing is much smaller than the mean free path. So this distance is generally in a gas smaller, much smaller than the mean free path itself. As long as you're at scales there, you can neglect the nonlinear term. So this is not a strong coupling problem at all. It's a weak coupling problem. The thermal fluctuations remain weakly coupled. In a liquid, it's similar because then the inner particle spacing and the mean free path are comparable. And so as long as you're at scales well above the inner particle spacing in a liquid, then again, you can drop this term. It's always weakly coupled. And so then the analysis can proceed along analyzing only the linear equation for the thermal fluctuations. And again, those are standard steps that people typically take on these problems because it's recognized that in much of the literature that this is small. Okay, so once we've done that, we now are going to say, well, we can't make any analytical progress on this because unfortunately we have to solve that equation. But we're going to follow Kraichnan saying, okay, let's model this turbulent velocity now by the Kraichnan velocity, the same one that Kraichnan used. If we do that and we replace the real turbulent velocity by Kraichna's, then we're back on very nice territory because now ignoring this fluctuation term here, that comes from the molecular fluctuations of the concentration field itself, we just have to analyze a Kraichnan model, and we have lots of tools for doing that. Okay, so that's what we did hereafter, is we analyze those equations. Now we have to look at the high-Schmidt limit. So we do exactly what Donev and vanden-Eijnden did there, but we have this new part, which is the turbulence part, and we have to see how to scale that in terms of the asymptotics. And of course, we know that the turbulence also depends on the shear viscosity. The viscosity matters in the turbulent flow, and we have to decide, therefore, how to scale the turbulence at the right order. And we know that the energy dissipation is given by this formula, which connects the Kolmogorov scale strain rate to the viscosity. And therefore, we said you should have to scale this based on this relationship so that you get a finite total amount of turbulent energy dissipation in a macroscopic or diffusive time, so on the time scale of the mass diffusion. And so that settled how this thing should be ordered in terms of the asymptotics. And then that just leads directly to this scaling of that white noise term for the turbulent case, the Kraichnan part. Of course, we also have to put in something to drive the scalar cascade. And so we put in a term. This could be done many different ways. Mean concentration. It could be done with a deterministic stirring force that injects concentration fluctuations. We wanted to make our life as simple as possible, so we just did it with a random stirring. So this is something often done in theoretical discussions, and we decided to do that too, just to make our life as easy as possible analytically. And so then we get our rescaled equations very similar to those that were obtained by Donev and vanden-Eijnden, and we do the same asymptotics. It all goes through, and the point is that when you do the asymptotics, now in the end you get exactly this Kraichnan model here. This is now the thermal part that Donev and vanden-Eijnden had, but we also have the turbulent part as well. They both exist in this limit. And this is now, we have to analyze this equation. And again, very similar to what happened with Donev and vanden-Eijnden, this is Stratanovich. If you convert to Ito, you get the bare diffusivity is sitting there. You get this renormalized diffusivity from thermal fluctuations. That's sitting there. You also get a turbulent eddy diffusivity, and all those effects coexist. And to make our analysis to begin with, we're going to drop this term, because this term is only going to be important at very, very small scales, and we can't do anything analytically with it. So we first of all drop that, and then we're going to go back and reconsider it after we consider this leading part. Okay, so for the moment, I'm just going to drop that term and then proceed mathematically, because now it's a Kraichnan model and we can just solve it. Okay, so we go back to our closed equations. When you're in a steady state with statistical homogeneity and isotropy, that equation can be reduced to quadratures, and here's the equation. For this particular covariance here, V that we have, this is the solution right here. This is what you have to solve. You just have to integrate this to get the covariance. And then once you integrate that, then you do this thing to, this transform here to get the spectrum, and then you're done. Then you know what happens at least within this model. So just as a sanity check, you can say what happens if I have no thermal fluctuations. That corresponds to setting this molecular radius, the solute radius, to 0, and then we immediately recover Kraichnan's original prediction from his early papers in 68 and 74. Okay, so that's just a sanity check saying we didn't make a mistake. But you can also go ahead and solve this problem exactly. So it's just a little bit of classical analysis. So you can do this integral by partial fractions. I mean, you have to use Vietta's formula to factorize this cubic. You can do those integrals. They're simple. It's not quite as simple to calculate the Fourier transform. If you use first the 1D spectrum, which is given by the cosine Fourier transform, we couldn't find any of these integrals in any of the standard tables, but we were lucky because these two terms, this one is not so hard. You can actually reconstruct that one from standard things in the tables. This one was trickier. We couldn't find any of these in standard tables, but luckily they're the real and imaginary parts of an analytic function. And so it turns out that this Fourier cosine transform you can just see as a complex contour integral along this contour of that analytic function. And then to evaluate it, you just shift contours. And these contours here are in the tables of integrals. And it turns out you can reduce the whole thing to auxiliary sine integral functions, and you get a closed analytical expression for this one-dimensional spectrum. And then you can take the appropriate derivatives to get the three-dimensional spectrum. So that all works out. But you can understand the basic phenomena without using the analytical calculation. We did that just so we knew exactly how you made the transition from one regime to the other. In the viscous convective range, if you take this equation, you can easily see that these terms are small. I mean, R is much bigger than the solute radius, the molecule radius. When you're at scales much bigger than the Batchelor scale, this term is negligible. You just get a really simple equation. You can integrate it. It gives the logarithm. So you don't need to set sigma to 0. As long as you're in this range, you recover the logarithmic behavior of the correlation function, and you recover Batchelor's 1/k spectrum. that's reassuring, but it's a little bit puzzling because I'll remind you that the whole theory of Batchelor and Kraichnan was based on assuming that you've got this exponential fall off in the energy spectrum. And now we're saying, no, there's a thermal spectrum there. And it looks like this 1/k doesn't care about that thermal fluctuations at all. That seems quite puzzling. Why should we get 1/k? Well, in fact, there's an enormous effect of the thermal noise here, but it's exactly the same as in a laminar flow. So it's already known that in laminar flow, the thermal fluctuations renormalize the diffusivity. In fact, the bare diffusivity that you get from kinetic theory, like Boltzmann equation, does not predict at all correctly the diffusivity that's actually observed in liquids. It's wildly wrong. And that's because you see all the effects of those thermal fluctuations renormalizing the diffusivity, leading to that Stokes-Einstein relation. And that happens in a laminar flow. So if you go and you measure the diffusivity in a macroscopic laminar flow and you read off what that diffusivity, that's already taking into account the thermal fluctuations. And so therefore, you get the correct answer here because the main effect in this range is just that renormalization effect of the bare diffusivity. However, things are very different in the viscous diffusive range. Okay, so if we now take this and we go into the viscous diffusive range, then again, we can expand this. We can look at the terms here now, expand this to leading order. We can now look at this expression that we get at leading order when R is much bigger than sigma. That term is small, R is much, this is small. This is the leading order term, but these two terms are analytic in R, in X, Y, and Z. So those are analytic. The term that's important is this one because that one's the one that's non-analytic. And when you take the Fourier transform, that's the one that dominates. So these are associated with Kraichnan&'s exponential decay spectrum. But this non-analytic term that comes from the thermal noise produces a 1/k² spectrum, just like what you expect from giant concentration fluctuations. And in fact, I'm going to pin that down more precisely and show how well this agrees with what's expected for giant concentration fluctuations. But anyways, so let's first of all just say, where does this come in? So when does, I've now done it, I said that it comes in when you're at R, much smaller than the Batchelor scale, but where exactly does the transition happen? Well, you can just match the two spectra, the Kraichnan prediction and this, yes?
Yeah, I mean, I see the theory and you say LB much larger than R, much larger than sigma. Can you go back one transparency to sort John Bell computation? How many decayed results? I mean, we say large. I mean, what's this ratio between LK and R and LB when the resolution is 100? You know, like
well,
2 decays only. I mean substantiation.
Sure. I mean, well, of course. I mean, I should say, I mean,
simulation of only like 100 modes. I mean,
well, I mean, yeah. So it's like a square root of Schmidt number. That's the ratio, right? So if you're looking at 1,000, you know, take a square root of 1,000, and that's the ratio. But I mean, what I'll show you in a moment, let me show you the exact analytical result. Because,
I'm talking about numerics because you're missing it in the substantial numerics. There isn't 1,000 modes.
No, well, but I'm saying, I mean, the numerics, we can treat the case you're talking about. We don't have to take a wide scale ratio because we solve the problem exactly, right?
Okay.
And, right, and so we know analytically what happens even when the scale ratio is not big, and I can show you that stuff.
I understand the analysis. I was just basically trying to understand the support from numerics. Is this really enough convincing? That's my point. Continue.
Well, but I mean, we're not. I mean, what I'm talking about is not numeric. I mean, well, I don't know. Are you talking about our numerics?
No, this picture of Bell, you know, I mean, like there's.
Oh, you're talking about with Bell. Of course, Bell did not study any of the stuff that we're talking about here because he didn't put in a scalar, right? But this is just for the velocity field here. And so what I was showing here was just the fact that you do not see the expected exponential decay of the energy spectrum. This is the k² thermal spectrum. So if you're asking questions about whether you can trust John Bell's simulations, okay, then we can have a separate discussion about that.
I'm not discussing. I'm just basically seeing that it's only 100 modes, and you can interpret. You can fit any curve of any slope for 10 modes, for 5 modes. You know.
I'm sorry. So what curve are you talking about? The green one? The green one is the thermal energy, is the thermal spectrum, and this is the prediction from statistical physics, and it's dead on what he sees.
Let's continue with your lecture. I just missed
Okay, yeah, so I mean, we can, okay, we all have to talk about Bell simulation then, but okay. Okay, so anyway, so you can easily see where the exponential Kraichnan, just matching them, doing a back of the envelope calculation, a sort of simple way of checking. You can guess where they cross by just saying, let's take this and match it to the exponential, and you solve that. And you find that the crossover is always just a little bit below the Batchelor scale by a factor of 10 or so. So it's right, you don't have a long, according to this argument, range of exponential decay below the Batchelor scale. Right around the Batchelor scale, you should see these 1/k². And that's what we then see in our analytical solution. So the analytical solution is the solid black line. The green dotted is Kraichnan's prediction. And the red dotted is what I got from that asymptotics for below the Batchelor scale. It's actually a little bit, in some ways, for the mathematics, we did all this hard mathematical work to get the exact result. It turns out that the asymptotics are so damn good that if you simply add the 1/k² part to the Kraichnan part, you virtually reproduce exactly what we did from our analytical calculation. And so after all that hard work, it verified that the simple asymptotics almost gives perfect answers. I mean, our formula in terms of the sine integral function tells exactly what happens in this transition region, but it's very close, just adding the two things together. Okay, so now we still have not taken into account, however, that other thermal term, the noise term in the concentration field, but that has a well-known effect anyways at high wave number. It just produces an equipartition spectrum for the concentration field, and that's easy to compute, and we wrote it here. And so what you expect then is that at sufficiently high wave number, that will come to dominate. And so again, you can find out where that will happen, and you just equate the giant concentration fluctuation to the k². This is our, again, there's nothing deep here. This is just where we guess that will transition over, and that's at this wave number here. And so then our final picture is that this is what will happen in the real world for the Batchelor range, a Batchelor-Kraichnan range of the passive scalar. You will see the 1/k. Then you'll start transitioning to something which is steeper. And by the way, these are the detailed predictions we worked out using the known parameters for water glycerol. And that was a considered choice because the best choice of testing these ideas is with John Bell's numerical code, and he's set up for water glycerol. So anyways, you then go very quickly after the Batchelor scale, just within a factor of 10 or so, you go to these giant concentration fluctuations, and then ultimately you go to k². So one thing interesting from the point of view of statistical physics is that these giant concentration fluctuations are not cut off by buoyancy as they usually are in laminar flow. They're instead cut off by turbulent shear. This effect is known also for laminar flow, but it's much weaker. And so not surprisingly, the turbulent shear is much more effective than gravity in cutting these off. And that's what happens according to our calculations. We also estimated the size of the buoyancy effects, but they're just very weak compared to the turbulent shear. Okay, so just to compare with standard theory and show that we really do reproduce exactly what's expected from the theory of giant concentration fluctuations, we can rewrite our result by using this relationship that relates the concentration gradients to the scalar dissipation rate and the diffusivity. And if we do that, we get this nice formula, which in some sense is nice because it's sort of purely geometric. But then if we also use the Stokes-Einstein relation, it takes this form. And that matches almost exactly to what's calculated with linearized fluctuating hydrodynamics. I mean, and the discrepancies are easy to understand because the typical situation that people look at is a case where you have an imposed mean concentration gradient. It's a fixed concentration gradient with a fixed magnitude, but in our case, the concentration gradients are random. They're isotropically distributed and they have random magnitudes. And that seems to account for the factor of 2/3 disagreement that we get with linearized fluctuating hydrodynamics, the standard calculation. And so the important thing is that the prefactors, except for that factor of 2/3, are identical. So it's exactly what you would expect from the giant concentration fluctuations here. So we're pretty convinced that that's what we're seeing in this calculation. However, there's a mystery here, or a puzzle again, because why the heck should we be using in this calculation D rather than D0? Is actually very well known for the Kraichnan model that this balance relation that I was using here is not what happens. What happens is that it involves the bare diffusivity. And the reason that we're not using this relation that comes from the Kraichnan model is, as I'll remind you, the Kraichnan model is not the real model we're trying to solve. We've done an ad hoc dropping of this term, the one that I crossed out here. And that's what's producing that k-squared spectrum at high wave number. So if you put that in, well, of course, then the concentration gradient doesn't satisfy this relationship anymore. And in fact, the concentration gradients become strongly cutoff dependent, which of course is well known in fluctuating hydrodynamics, is all those quantities become very dependent on the cutoff. And so then the question is, well, but if this is cutoff dependent, again, how can I use this relationship here? Because this thing should depend on lambda. Well, you have to understand what this thing actually means. What is the right concentration gradient to put in? And the point is that if I take our solution of the Kraichnan model and I calculate from that, this covariance, the gradients, just by applying the Laplacian, that's a simple calculation and you get this formula. And you see that there's a long range of scales from the Batchelor scale, by the way, which is typically microns, down to the scale of the solute molecule. So, you know, for something which is like water glycerol, that's literally nanometer scale. So you have this big range of scales where these concentration gradients are essentially constant. And so if you measure the concentration with some space resolution, I'll call it L, and you model that by just mollifying, coarse graining at that scale, then what you'll see is that those coarse grain gradients in this model are essentially independent of scale over this big range. Now, that can't be true in the full model because we start seeing the effects of those k-squared, but that means that this relationship still holds over this range of scales, which is a long range of scales, a pretty decent range of scales. I showed it before, from here to here. Okay, so from Batchelor scale down to this scale, over which the measured concentration gradients will be independent of the scale. And so that's what an experimentalist would measure if he looked at any resolution over that range. And that's the concentration gradient that actually appears in our relation. And so if you use that concentration gradient, what we call the effective concentration gradient, then we get this good agreement with the standard theory of giant concentration fluctuations. So I'm going to try to end this up and say that the same puzzle, I'm going to circle back now to Navier-Stokes. The same puzzle also appears in Navier-Stokes. Since we are arguing that the correct equations for molecular fluids are not deterministic Navier-Stokes, there are some, I mean, the Landau-Lifshitz equations are viable. Navier-Stokes is not, deterministic Navier-Stokes is not. Then the usual energy balance that you do with deterministic Navier-Stokes is not correct. So what is it if you use these equations? Well, it's a really simple calculation. If you just use Ito rule, you can calculate this. This is a white noise force here. You can just apply Ito. This is what comes out. This term here on the far right is what comes out of the Ito change of the chain rule. Everything else is standard calculus. And this is exactly what you need. This is exactly what's expected here. Because if you're in a glass of water at rest, I mean, thermal equilibrium, homogeneous thermal equilibrium, and you take an average, well, these time derivative and space derivative terms all vanish. This term vanishes because it's Ito, and the balance in the steady state is that the viscous dissipation is coming from here. And so this term should match onto the viscous dissipation, and that's exactly the viscous dissipation that you get from the equipartition spectrum. So this is exactly the right thing. This is saying this is what you need to have in this equation. Well, that's nice for a glass of water sitting at rest, but how then can we use how do we justify using the deterministic Navier-Stokes in order to make the standard energy balance that we always do when we're looking at energy dissipation in a turbulent flow? And so to try to explain what I think is happening there, let me just use a simple model spectrum. This is the easiest way of explaining this. So I'm going to take a simple von Karman model of the whole spectrum, including the thermal part. And then I multiply by k squared, and that's what I'm plotting here. So this is the entropy spectrum. And the important thing about that is this entropy spectrum is that there's a huge valley here around the Kolmogorov scale. So this is where you would predict that this transition happens according to using the Lambert W function anyway. So the point is that what that line represents, you got this deep valley. So now if you integrate to get this effective concentration, this RMS concentration gradient here, you do this integral. What you see is that, of course, it grows as you go through the turbulent range. That's expected. The gradients are getting bigger and bigger. And then there's this 3-decade-long plateau right around the Kolmogorov scale, where those effective gradients in mean square are independent of the cutoff. They don't depend on the cutoff at all. And then you have to go down here before they start seeing that equipartition spectrum, before that becomes sufficiently large. And so if we go back, this term, you can also, by a similar argument using Ito isometry and mean square, you can estimate that term. And anyways, it also has mean 0. This is the bigger term. That one is, they're both 0, they're both small. And so to a good approximation, you can argue that the standard energy balance comes out in this equation. If you integrate out all the scales above lambda, that will renormalize the diffusivity, but it's not a huge effect. It's sort of, it's well known the renormalization of the diffusivity is not a big thing anyway. Unlike for the diffusivity, it's fairly small. And so you'll get out the standard energy balance. However, that does not mean that Navier-Stokes is correct. In particular, if you do the same thing for higher order gradients, the story is totally different. If I now do exactly the same calculation, I don't multiply this by k squared, but I multiply it by k to the 12th, what I would get by looking at the fluctuations of the 6th derivative. Well, then when I look at that integrated quantity here, it never has a plateau. And you'll go up through the inertial range. When you get to the Kolmogorov scale, it immediately starts filling the thermal fluctuations. And then you go to this range here that is what you calculate from the k squared spectrum. And that's completely consistent with what we found with John Bell, which again, you never see the predictions of deterministic Navier-Stokes, which are these lines. You only see the thermal fluctuations. And it got that gets better and better as you look at higher and higher order gradients. So that's consistent with what I was saying before. Okay, so these are my specific conclusions. I have sort of 3 conclusion sides. I mean, these are specific conclusions. And I think these are things that I'm throwing out for further discussion. I think I've already tried to show that the thermal noise drastically changes the predictions in below the Kolmogorov scale, in particular sub-Batchelor. I think this is just prototypical, however, of many other processes involving sub-Kolmogorov scales. I mean, all the problems I mentioned before, there should be a real competition in sub-Kolmogorov scales between the turbulent effects and the thermal noise effects. They'll compete in very interesting ways that we need to figure out. I'm going to say again, I don't think, I mean, Landau-Lifshitz fluctuating hydrodynamics may also break down. In fact, I think there's a very good possibility that it will, but it's a physically relevant model of sub-Kolmogorov scales, and deterministic Navier-Stokes is not. It simply misses important physics. So that doesn't mean engineers shouldn't use it. I mean, Galerkin truncated around the Kolmogorov scale, direct, deterministic Navier-Stokes. That's what I'm calling. It's a nice convenience that deterministic Navier-Stokes also gets abbreviated as DNS. But anyway, I mean, deterministic Navier-Stokes should be a good model for the inertial range in larger scales. But when you start pushing this below the Kolmogorov scale, I consider all of those as unphysical virtual reality simulations. And it's highly questionable what of that will carry over to real molecular fluids. And another consequence that I think is important for this group to discuss is that I think that therefore weak solutions of Navier-Stokes a la Leray are just unphysical. I mean, if you introduce an ultraviolet cutoff as physically required, then existence, uniqueness, and regularity are immediate. And that's also true for the Landau-Lifshitz equations. All those problems are easy to solve as soon as you put in that cutoff. You have nice, strong statistical solutions. So I think, and I'm going to say again, I think the Clay Millennium Prize problem has nothing to do with real world turbulence. It's the wrong question to ask. I think that PDE theory plays an important role, but those are not the correct weak solutions. This doesn't change the picture of the inertial range. And in fact, the Onsager theory and so forth should still carry over. And I would say those are the correct weak solutions in the high Reynolds number limit, where you go back to essentially a PDE description as the inertial range gets longer and longer. And so I'm going to say what my big lessons from this work, what I learned from it, is that the mathematics of turbulence is not only PDEs and not SPDEs. I mean, I think that mathematical work, especially for these small scales, is urgently required on problems of foundations of hydrodynamics, Zwanzig-Mori theory, nonlinear Landau-Lifshitz equations. There's a lot of work going on that already, but not so much attention to it being paid in the turbulence community. And I think that has to change. And the other big message, of course, is that laboratory experiments are really urgently required here. I mean, so we're lucky that we have good computational tools for studying these things, but still, we don't want to substitute one virtual reality for another. And ultimately, what we need to understand these fine scales of turbulence is experiments. And what we can do until we get those, which is really hard, I think, is pay more attention to existing experiments on laminar fluids that probe those small scales, so we can get some essential clues about what might be happening. And then lastly, I'm just going to end with this quote from Feynman, where he, in his Feynman lectures on physics, made the point that if there was some cataclysm and all scientific knowledge were to be destroyed, the most important thing to hand on to future generations is that matter is made of atoms. And he says in that one sentence, you will see there is an enormous amount of information about the world if just a little imagination and thinking are applied. And so I think that's a good lesson to carry on in our discussion of turbulence and its mathematical foundations. Okay, well, I thank you very much for your patience and your attention, and I'll be happy to discuss all this more.
Gregory, I have to go. I have to teach, so another time. Okay.
Okay, absolutely.
Questions from the audience? Okay, how about, do we have any? Okay, if not, then I have a quick question for you, because it's getting late here. I mean, when you're basically saying that, well, we have the computers and computations, etc., and we're substantiating some of the evidence on computations. For which Reynolds number and how high is the resolution, so that I can really trust that these numerics really supporting the beautiful theory. Theory is theory, theorems are theorems. But because you are really trying to support the theory by numerics, how big is the Reynolds number used? Because you're talking about Euler, this number is very, very, very high. And how good is the resolution that I've been using here?
Sure. Yeah, by the way, I just want to mention that all of these papers are now appeared. So John Bell's was accepted in Journal of Fluid Mechanics, and it was reviewed. I mean, I was a co-author on that paper, and this was a question that was asked by our reviewers as well. And John Bell, okay, but I'll just say that what John Bell could do with his simulation, the highest Reynolds number he could get up to was bulk Reynolds number of 554. So it just barely has an inertial range. But that wasn't really the point, because he was more interested in the dissipation range, which appears already at relatively low Reynolds numbers. So the whole point of his calculation was not to study the inertial range, it was to study the dissipation range. Pardon?
For not so high Reynolds number.
For not so, that's, yeah, they can't do it yet at higher Reynolds number with his code. That was the best he could do. I mean, things are going to get better, obviously, and they'll be able to go up to higher Reynolds number, but they're like 10 years, behind what you could do in, in deterministic Navier-Stokes with the fluctuating hydro code. But I mean, I agree completely with you that, I mean, in the end, the only way to settle these issues is going to be with experiment. And I think that mathematics, I mean, I don't know of any rigorous argument, and we discussed this in our papers. There are lots of rigorous theorems that purport to show that deterministic Navier-Stokes equation is valid. I mean, and these are friends of mine, people like Bardos and Livermore and Quastel and Yao. But if you look in the details of those arguments, they don't work. They prove theorems, but they don't apply to the real world, because it turns out, I mean, they're all based on the scaling property of the Navier-Stokes equation, incompressible Navier-Stokes. And they say, well, if you let the system get big enough and the velocity get small enough, then eventually you'll see deterministic Navier-Stokes. And I agree, those are rigorous theorems and they're fine. But then you say, well, how big and how small do you have to make it so that you get rid of this k-squared spectrum in the dissipation range? And if in the atmosphere, it turns out to be impossible. I mean, like in the atmospheric boundary layer, if you wanted to increase that range where you see deterministic behavior by a factor of 2, you would have to increase the size of the atmospheric boundary layer by 250,000 and decrease the magnitude of the velocities by 250,000. And so in practice, the theorems don't apply in the real world. And so I'm not aware of any rigorous theorem that justifies deterministic Navier-Stokes at those scales.
Okay,
And so
and another question, Greg, here, before people will need to go. So, I mean, some people, I will stay here, but some other want to go. But there was one more question, and then we see, let people go if they want to go.
I have actually a very trivial question. Since you use the word deterministic, I am assuming that Landau-Lifshitz equation has a stochastic term. So
von Karman, I'm sorry. No, I didn't understand. I'm sorry, von Karman, stochastic. I don't understand the question. I mean, there was nothing. So the
governing equation that you're solving.
Oh, the Kraichnan model?
No, how are you performing the numerical simulation? There is, if you're not solving Navier-Stokes, then there is some other equations that you're solving, right?
Well, there were lots of equations, so I'm not sure which one you're referring to. So, and the equation that I spent most of my time discussing was our Kraichnan model. Of course, it has stochastic terms in it. So this equation here was, so the starting point of all the analysis. Oh, you can't see it. I'm not sharing anymore. Sorry.
Okay. Okay.
We are sharing. We see it. We see it.
Oh, you do see it. Oh, I am sharing. Okay, sorry.
Two questions in here. One, I believe if it is a stochastic equation, so there is a noise term, and I believe noise is going to be a non-Markovian quantity. So if I go about constructing one for a given flow, I don't believe that is a very generalizable argument over there. So
I'm sorry. I'm sorry.
How do you go about constructing that noise term?
How did we get this noise term?
Yes.
Well, okay, so this is, we didn't construct this ourselves. This is standard in the statistical physics literature. It comes from what's called the fluctuation dissipation relation. And there's literature on this for, 50 or 60, 70 years. So we did not construct it ourselves. We just took it out of the literature.
Yeah, but fluctuation dissipation is still ongoing and is still a hot topic. And that's my understanding. Please correct me if I'm wrong.
I'm sorry, what are you asking? It's hard for me to hear you. Say again.
Oh, sorry.
Maybe go to
Go closer to the microphone there. Just not enter.
So are you asking that are there open questions about the Landau-Lifshitz equations and their validity?
I believe there are open. It's still a hot topic when you talk about fluctuation dissipation. That's my understanding, but I could be wrong. So please correct me. But that's my understanding. You can have a nice theorem, but when you go about have constructions, that's still a hot topic.
Well, as far as the fluctuation dissipation for the Landau-Lifshitz equations, I'm not aware of any experimental discrepancy between the Landau-Lifshitz equations, the predictions of the Landau-Lifshitz equations, and experiment. None. And there have been a huge number of experiments. Look in the book of Zarate and Sengers, for example, our University of Maryland colleagues, and they document all of this. Of course, there are always questions. It's a physical theory. But there have been decades and decades and decades of predictions made by this and comparisons with experiment. Among other things, onset of convection, which was a big issue that was raised by Hohenberg and others in the 1980s, was ultimately resolved by Ehlers, who showed that there was an apparent discrepancy with the onset predicted by thermal fluctuations there. And he ultimately showed that it was because of experimental problems that he solved. So again, I'm not aware of any experimental discrepancy of the predictions of these equations at all.
Yeah, but that does not mean that that's a general, that is a generalizable. But let me tell you, why do I find it a little unsettling?
I just want to say, I mean, of course, it's a physics theory, and any physics theory can be wrong.
Greg, sorry, I mean, we are really, it's 20 minutes past 5. Some people would like to leave. So let us thank Greg again, and you can continue the conversation. I mean, I'm not going to stop the conversation, but at least I would like to get a chance for those who would like to leave before they leave to thank you. Okay, thank you again.
Oh, okay. Well, thank you for your attention. I'm happy to have you.
With the discussion. We are not leaving, so you can continue the discussion. But those who would like to leave, I would like to give them the chance.
The thing is that the reason I find it a bit unsettling is because all right, if you're going to look into the statistics, the statistics may match. But when you look at the pointwise quantities and you look at the instantaneous fields, that's something that I'm a little skeptical about it. For example, I can construct to give you a trivial example, I can construct a Markovian process. I can construct a non-Markovian processes. Both the fields will look entirely different. But I can still. But when I look into its statistics, the statistics will be very identical to each other. But these two processes are entirely different. So that's one thing that is generally very unsettling for me when we have noise terms on it. But I could definitely be wrong. So if you have any thoughts on it, please tell me.
Well, okay. So I mean, so first of all, there are rigorous mathematical results about this. I mean, among other things, my postdoctoral advisor Herbert Spohn. So in the context of Boltzmann equation, I mean, the Boltzmann equation, deterministic Boltzmann equation, also is not correct, and it's well known that it has fluctuation terms. And those have been rigorously derived by my postdoctoral advisor already in 1983, Herbert Spohn, in the Lanford limit. I mean, so in Lanford's approach, this is with this in this low density Bogoliubov grad limit. And then for a third of a mean free time, you know that as a law of large numbers, you get out deterministic Boltzmann. But then there's a central limit theorem correction, and that's described by the linearized fluctuating Boltzmann, and that's a theorem. And more recently, Laurie St. Ramon and her collaborators have extended that work and have also investigated large deviations, which was actually something that my Simons colleague, Freddie Boucher, has made an important contribution to. So that we have known cases where these kinds of fluctuation terms are rigorously derived. And once you take the fluctuating Boltzmann, I mean, it's been known since the work of Fox and Uhlenbeck in the 1970s, that then you get out the Landau-Lifshitz equations from those. So, okay, I mean, so there's a lot of background work. I mean, this is not just pulled out of thin air. There's decades and decades.
I'm not accusing of putting things. I'm just trying to understand it. I want to focus on your keyword at long limits, because central limit theorem works on at long limits. So at long limits, everything will have some stable density. That's okay. But then I can construct more than one processes that actually converge in distribution at those things, and all of these processes could be very, very different from each other.
But I'm saying, the sense of derivations of these results, they're dynamic.
If my rigor is based upon at long, just describing the long limits, then
it's not
this is a non-unique problem. I can have 100.
I'm sorry. Okay. Let me try. So first of all, the central limit theorem is not long time. That's not the average that's being considered. It's the central limit theorem is in this Bogoliubov grad parameter, which is a dimensionless density. So the small parameter that gives the validity of the Boltzmann equation is the particle density multiplied by the radius of the molecule cubed. So this measures basically the probability of seeing two particles at the same location. And that's the small parameter that gives the validity of the Boltzmann. So when you look at, all of your large deviations and so forth is in that small parameter. Okay, that's the small parameter that's relevant for the kinetic theory. So this is what Lanford did in his work, back in the 70s, and then been extended by many, many people. And what's known is that you have a law of large numbers when that parameter is very, very small, but then there are corrections of order the square root of that parameter that govern the central limit theorem. And these are dynamical results that give out rigorously a linearized Boltzmann equation with a white noise forcing in it.
Okay, I think if you just help me out with some references,
Sure,
so
I'll be happy to provide references.
I could do some reading on it. Otherwise, we are now going a little orthogonal from.
And by the way, in models,
so it's better if I do my reading than yeah.
I mean, I would also recommend looking at Herbert Spohn's book. So Herbert Spohn has a nice book, Large Scale Dynamics of Particle Systems. And he has this is old now. I mean, it's several decades old, but it still has a nice discussion of a lot of the relevant mathematical literature. And in particular for lattice gas models, where there's been a lot of work on deriving the hydrodynamic approximations. There are many, many papers that have discussed these Landau-Lifshitz equations.
When you talk about the lattice gas model, it's basically you're talking about the modern day lattice Boltzmann sort of a thing, right?
Do you mind?
Well, not lattice Boltzmann, but stochastic.
I have questions.
The lattice gas, Kawasaki. Kawasaki lattice gas models, that sort of thing.
Okay, somebody else also has a
Greg,
question.
sorry to interrupt. So I had a couple of questions related to your talks. The first one is, tell me if I rightly understood that the fact that you have a cutoff, the big lambda cutoff, is due just to keep a finite amount of energy in your system. That's right? You said that physics is justifying that there is a cutoff at small scales, and this is just due to the fact that you want energy to be finite.
Well, there are formal derivations of these equations using Zwanzig-Mori, methods, going back again decades. I mean, the earliest paper I know was by Zubarev and Morozov in '83. They were one of the first people to derive this. And whenever you do those, you're automatically doing some coarse graining because these are only supposed to be some effective description. That cutoff is arbitrary, but it's necessary to the derivation. You cannot have hydrodynamics if you're not coarse graining at scales much larger than these molecular scales here.
Yes.
So yeah, I mean, the point is that
it's of the order of the mean free path.
That's right. I mean, you have to be large. You have to be coarse graining at scales much larger than the mean free path in order to have any hydrodynamic description being valid. But it's not a deterministic hydrodynamic description. It's got stochasticity in it.
Yeah, sure. And then the second question was related to: do you think there are some situations where the the thermal noise will hit inertial range physics?
Well, that's an interesting question. I mean, I guess we're writing a paper about that now, where it hits it, but only in a rather subtle way. There are claims that it may hit it more seriously. We did not see any evidence for that in any of our work. As far as we could see, all the statistics of the inertial range was unaffected by thermal noise. So we didn't, and this was also consistent with what John Bell saw. I mean, if you go back and you look at his plots, I mean, basically, there's the deterministic simulation is in black. Then he has a stochastic simulation in red, and in the inertial range, they just overlap perfectly. And that's not only true.
But your Y scale is very compressed because you have
that's true. But I mean, in our shell model, we also did this as well, and we looked at it in great detail. And there's just basically no difference. I mean, in the inertial range, they're dead on. I mean, it depends on what statistic you look at, of course. I mean, the energy spectrum might be less sensitive to it than other things. We looked at other quantities like inverse structure functions turn out to be more affected, and they are affected already at scales in what would be traditionally called the inertial range, but it's all you have to look at more refined quantities to see some direct effect of the thermal noise inside the inertial range, or even at the bottom of it. I mean, so
do you think that this thermal noise will be enough to trigger some spontaneous stochastic behaviors?
Absolutely. In fact, that's what we're writing our paper about. So in fact, we have compelling evidence in shell models that happens, that indeed thermal noise alone This is, so again, it doesn't change the statistical behavior of the large scales, but what it does do is it makes the dynamics totally unpredictable. And if you start off with fixed initial data and you consider the high Reynolds number limit, the solution stays random. And we have very strong evidence for that in our shell model calculation, that in the high Reynolds number limit, you go to an inviscid model. It's like the analog of Euler, but the solutions stay random.
All right, more questions? Sorry. I mean, I suggest, because we need to leave, I suggest that you contact him. Maybe you can have Skype talk or Zoom talk or something like that, or because I mean, I think.
Sure.
Thank you.
Thank
So
you.
just, anybody that wants to talk more, shoot me an email. I'll be happy to talk more.
I mean, you can do Skype, you can do Zoom together.
Absolutely. Whatever, yeah.
Thank you very much again, Greg, for
Okay,
the
thank you.
very exhaustive. Bye-bye.
Okay,
Thanks, Greg. Bye-bye.
okay,
Thank
bye-bye.
you for staying to the end. Oh my.